to the Phoenix Controls demonstration facility. We have invested in equipment that will duplicate what you would see in real-world environment for several different applications. Where I'm standing right now is a wet chemistry lab application, which you would typically see wet chemistry fume hoods, general exhaust and supply air that is being controlled in this space to maintain the safety, to gain the best savings that you can for these type of environments, and also to give your customers the satisfactions for the product that they're using. So what I'm standing right next to, this is what we call our smoke demonstration fume hood. And what this is a 6-foot combination fume hood. And what I say by combination, I mean it has a vertical moving sash, and it also has horizontal moving sashes as well. So the combination of the vertical movement and the horizontal is what we would typically call a combination fume hood. In this type of an environment, what the purpose of the fume hood valve is, or the Phoenix Controls Venturi valve on top of the fume hood, is to guarantee the safety of the occupants that are using this fume hood. So the fume hood has to adhere to certain standards that allow a certain face velocity of air, which is an average of amount of air going across the front of the fume hood at a given velocity at all times. It also has to maintain a certain speed of response to guarantee that as I'm moving these panes around, that my valve can track where the hood is going at all times to make sure that I'm maintaining safe containment inside of the fume hood. So the three things that Phoenix Controls really does for the safety aspect of fume hoods by using our valves and our sash sensing technology is giving the customer the fastest speed of response. So the ability for the fume hood valve to be able to react to a movement in the sash position, whether it's vertical or horizontal, within 1 second speed of response. So that means if I move this sash, by the time I stop moving the sash, within 1 second, my Phoenix valve is going to finish positioning itself and be in a steady state. That means that no matter what I'm doing inside of this fume hood, almost as fast as I can move the sash, my valve is going to react and it's going to settle out to guarantee that I have accurate and stable airflow control. The best thing about the Phoenix Controls Venturi valve is because they're pressure independent, I'm going to get very stable airflow control on top of the speed of response. So I can guarantee I have a 1 second speed of response to change in command. I can also guarantee that I have less than 1 second speed of response to changes in pressure that's going on inside the ductwork. So as I have other fume hoods in this lab and I'm moving them up and down, as the entire exhaust ductwork is all connected in a plenum, as one of those fume hoods moves, the entire pressure envelope in that ductwork is going to change, and it's going to require my fume hood valve to react to the pressure change in that whole scenario. So if I'm moving this sash up and down, my other fume hoods that are inside of the space are also going to be automatically reacting to the pressure changes in the ductwork by having the cone inside of the valve automatically change based on the pressure fluctuations. That's going to guarantee not only that I'm going to give you an accurate airflow at all times, but it's going to guarantee that I don't have to have my valve measuring to change for the velocity or the pressure in the ductwork and readjusting its position to guarantee accurate and stable airflow. So as fast as I can move this valve up and down, my actuator is tracking my sash movement within 1 second. Also, my cone inside of my valve is automatically adjusting to the pressure changes in the ductwork. So as this valve sits in its steady state, I don't have it hunting all the time to try to maintain a set point. It will go to its set point and it will stay there and give you an accurate airflow throughout the course of the day. It also guarantees that we have plus or minus 5% accuracy through all of our set points. So across the entire flow range, or what we like to call the turn down, the minimum and the maximum airflow on the valve, we guarantee plus or minus 5% of accuracy across the entire airflow range within our pressure requirements for the valve. So that's kind of how the valve works a little bit. So I'm going to turn on a smoke machine that we have in here. We use theatrical smoke to simulate chemicals inside of the fume hood. So as you can see, this is safe, non-toxic smoke. But we like to use this again just to show how the speed of response will react inside of a 1 second valve, and I can also show you what a 3 second speed of response, which is kind of the industry accepted standard, or a 6 second speed of response in this same fume hood would react. So as you can see, as I'm moving any one of the panes on this fume hood, I don't have any loss of containment across the face of this fume hood. And again, as I'm moving these back and forth, within 1 second, my valve is going to respond to the change in command and finish positioning itself. And I'm going to guarantee that I have containment within an instant inside of this fume hood, and I can guarantee I'm not going to lose anything as that valve sits in its steady state after the change of position has been achieved. So the speed of response, again, 1 second speed of response. So no matter what sash I move on this hood, within 1 second my valve is going to respond, and I'm going to guarantee that I can have that containment inside of the fume hood. You'll also notice that once it's in its steady state, I don't have any puffing effect or anything inside of the fume hood, which would be indicative of a case where a fume hood would be sitting there hunting to try to maintain its set point. Because the pressure independent aspect of the Phoenix controls Venturi valve, I get a very stable and steady control no matter what position I leave the sash in. The other thing you notice when I close this sash, you don't see extremely turbulent air inside of the fume hood, because just like when I open the sash, I need the face velocity to increase at the same rate that I'm moving the sash. When I close the sash, I need the face velocity to decrease at the same rate, guaranteeing that I don't have turbulent air which would knock things inside of the fume hood over. So again, as I open the sash, within 1 second my fume hood valve is where it needs to be, and you can see that everything is well contained inside of the hood. When I close the sash, you can see again that I have still good containment. Nothing gets out of the hood, but I also don't have very turbulent air inside of that fume hood. Now we hear a lot in the industry that 3 second speed of response is good enough. Everybody says, well, the standards say that within 1 second you can start to move the airflow control device, within another second you can get to 95% of its position, and then within another second you can get the last 5% of its position. So that's a 3 second speed of response versus 1 second, and I can simulate how that looks by putting a delay inside of our valve here. So what I'm effectively doing is introducing a 3 second step delay, which will simulate my sash moving, my valve moving to achieve 95% of its command within the second, and then within the third second achieving the other 5% of its command. So as I open this sash now, there's a lot of chemicals that are very lazily being sucked into the hood. There's also a loss of containment on top of the hood, and I'm losing containment out the front of this fume hood. So not only have I just compromised myself by having only a 3 second speed of response, because now me as the user, I'm breathing in the chemicals right here, but I'm also compromising the secondary containment zone, which is the rest of this room. Normally every chemical inside of this fume hood would be contained inside of its own hood, but now because only having a 3 second speed of response, I'm losing containment out the top of this hood, which is contaminating the air in this room for everybody else that's breathing it. Consequently, I also said when I close this sash that I will get very turbulent air if I have more than a 1 second speed of response. So I'll show that as well. You can see the air is blowing around very quickly inside of the fume hood. So effectively what happens when I close the sash with a 3 second speed of response, I get a very high spike in velocity going into the hood, which again, if I had beakers or paper or something on the front of this hood, I could be knocking those beakers over. I could be causing chemicals inside of the fume hood to mix when they shouldn't be, and it could be affecting the reactions that I'm trying to do inside of my fume hood. So that's a 3 second speed of response. I can also introduce a 6 second speed of response into this fume hood as well. So same type of delay where I'm stepping up the command over 6 seconds. And again, if you're using a flow measurement type device, even if you have a fast actuator on it, it's still going to take longer than that actuation time before that device is going to stabilize. So this is going to simulate if you had something that was a 6 second flow measurement device, which really doesn't exist either. But if I'm using something that has a 6 second speed of response, you can see now there's a lot more loss of containment here on the face of the hood. And I don't know if you can see it on the video, but there is a loss of containment, a great loss of containment coming out the top of this hood, because that valve is taking 6 seconds to respond when I'm moving the sash at the same rate I was previously. So conversely, when I close the hood, you'll see the air is very turbulent inside of the fume hood, which is going to cause that same issue with mixing chemicals or things to get knocked over as well. So I showed you the difference between a 1 second speed of response, a 3 second speed of response, and a 6 second speed of response. Secondary to safety of fume hoods is energy savings. Everybody realizes that fume hoods use the most amount of energy when it comes to any airflow control device inside of a chemistry lab. When you're using a single fume hood like this fume hood, when left running at 100% flow, could use as much energy as 5 small houses in the United States. So if I'm leaving this sash open like this, again, I'm guaranteeing that I'm containing my chemicals inside of my fume hood, but I'm wasting a lot of energy when this fume hood is left open. So at Phoenix Controls, we have designed some smart controls called usage-based controls, which allow a fume hood to set back to a lower airflow when nobody is present, even if the sash is left open. Now we call it a zone presence sensor. It is not strictly a motion sensor like you would think with most other products. The Phoenix Controls zone presence sensor, which I'm pointing to here, actually has an imaging chip built into it and an infrared generator. So it is not looking at Doppler shift radar technology like you would see with most other motion sensors. This device, when it's commissioned at the time the fume hood is commissioned, actually maps out an area in front of the fume hood that allows you to narrow down or widen the area that you're looking at in front of a fume hood to guarantee that this thing is not going to trip in and out of setback as a nuisance. So take for instance if I had a workbench sitting right in front of this fume hood 3 or 4 feet away, when a person is sitting in front of a chair and rolling back and forth, this thing is going to pick up their motion. Now that person is not working inside of the fume hood, so that fume hood does not have to run at 100% of its max capacity. It can actually drop down to a 40% reduction in its energy, giving it 60 feet per minute instead of 100 in this particular application, which will net you 40% energy savings just by putting this device on the fume hood. Again, if I had a wide range of motion Doppler sensor that was looking at 120 angle of view, what's going to happen is anything in front of that, in that 120-degree angle view, is going to get picked up as motion and trigger this thing to stay in full flow. So you won't be realizing the energy savings that you need. With the Phoenix Controls Zone Presence Sensor, I map out a very narrow window in front of the fume hood, and I can set the delay that this has. So I can set it as low as 5 seconds or as long as 5 minutes or 10 minutes if I wanted to trigger the setback. I can also trigger the sensitivity to make it work when somebody is only 2 feet or 3 feet away from the fume hood. It will still go into setback mode to guarantee that I'm not wasting energy or having nuisance setbacks. So right now this fume hood is running at 60 feet per minute versus 100 feet per minute. You can see there is still no loss of containment because of the stability of the Phoenix Controls product and the pressure independence that we have in our product. Now watch what happens when I step inside of that motion zone. Within a second, again, my valve is going to go up to its full flow, 100 feet per minute, and as I move my hand back and forth in this hood, I still have no loss of containment. So again, as I step back, within 5 seconds on this particular hood, it's going to go into setback mode, and it just dropped down to 60 feet per minute. Again, you can see that the chemicals inside of the hood slow down when it's at 60 feet per minute, but per the ASHRAE standards, having 60 feet per minute in that hood when nobody is in front of it is still acceptable, and I can prove it here by no loss of containment. Again, when I walk up to this thing, it's immediately going to go back to 100 feet per minute. So that's how the zone presence sensor helps save energy without any human interaction. The other nice thing about this particular device is if you're using this in low light conditions, so if I need to shut the ambient light in the room off and I'm still working in the fume hood, or in the case where I'm doing animal testing and I have to use something like a red light inside of the fume hood so the animal thinks it's nighttime, so the infrared generators that we have in this will actually project down onto the floor, and this device will actually work in pitch black as well. So it's variable based on the amount of room you need in front of a fume hood and the sensitivity of it, but it will also work in low light conditions as well. So that's one way that we save money. The second way that the Phoenix Controls products save money is through a function we call Hibernation Mode. Now if you're thinking about wet chemistry applications, again in pharmaceuticals or places like that, typically the fume hoods are assumed that they're going to be running 24 hours a day, 365 days a year because they're always doing some kind of testing. But when you get into applications where you might have a compounding pharmacy in a hospital, or you might have a teaching university where you have a lot of fume hoods inside of a room that might only get used 3 months out of the year, I don't need to run this fume hood at its full value all the time. So in this particular case, I'm going to assume that I'm in a teaching university and this fume hood is not being used at the particular point in time. I, as a maintenance personnel or a teacher, can come in, I verify that there's no chemicals in this fume hood currently, and I want to save energy. So based on ASHRAE Z9.5, you have to have a minimum airflow through a fume hood while it's being used. But if it's not being used, you don't have to pull air through it. So right now, I might be pulling 250 CFM through this hood, but again, I'm not using any chemicals, I'm not using this fume hood to contain any chemicals, so I can shut it off. So through the Phoenix Controls monitor, this is an older monitor, this is a 631, or through the Sentry monitor, which I'll show in a little bit, either one of those monitors, or through a building automation system, or if you wanted to hardwire a key switch on the wall, I can verify that this sash is 100% closed, there's no chemicals in the fume hood, and I can actually send this device to a full shutoff mode. So through a key sequence on the fume hood, I just shut this down to 0 CFM. And you probably can't see it on the camera, but this monitor actually indicates off. On the Sentry fume hood display, it will actually show fume in hibernation mode, so that there is no mistake that the fume hood is in hibernation mode, or in this case, off. Now you say, well, that's all well and good, I'm saving energy, but what happens if somebody walks up to that fume hood and doesn't know it's off, and they just throw the sash open and put chemicals in? Well, again, maintaining safety is our primary goal at Phoenix Controls. We can guarantee that this fume hood is smarter than the person using it. So again, in a compounding pharmacy or in a teaching environment, students don't usually get trained, or the personnel inside of the compounding pharmacy may not get trained on the specific equipment they're using. They may have just been told, if I'm using chemicals, I need to have it inside of a fume hood. So what we can do is actually guarantee that no matter what motion you make with this sash, it will take the valve out of its shutoff position, out of its hibernation mode, and put it back to its correct airflow. So if I move any one of these sashes more than 1% or a very small opening, automatically that valve is going to come back into motion, and I'm going to have my 100 feet per minute set point on here again. So even though we have safety and savings built into these fume hoods, the safety is always paramount. And because this just came out of shutoff mode and I closed the sash, it's not going to go back into shutoff or hibernation mode unless I reinitiate it on the fume hood display. So I'm always guaranteeing the safety of the people that are using the fume hood. The satisfaction of the equipment that we use here, because the Phoenix Controls products have no flow measurement devices in them, there's nothing inside the airstream that's going to get dirty or clogged, we have no maintenance. If you look in our documentation, the maintenance schedule says no maintenance required. We have products that have been in the field well over 20 years that have never been taken out and cleaned because the products just still work. Now we still tell people that it's a good idea to make sure, especially in fume hoods, that you have them recertified every year. Most facilities have a health and safety initiative that makes them recertify their fume hoods every year. And if you want a double check to guarantee that the Phoenix valves are still working properly, that's a good way to do it. So you can take a Phoenix Controls run fume hood that has a Phoenix Controls valve on it. You can actually shoot the face velocity on that fume hood on an annual or a semi-annual basis to verify that that Phoenix Controls valve is still working properly. So what you're looking at right now is the Phoenix Controls Sentry fume hood display. So going back a few years, we had an initiative to try to make our products stickier with the customer. And the problem with having a company that makes products that require no maintenance is once the products get installed, most of the time the customers forget what's in their facility. So for us to try to get back in front of the customer, we've been developing products that are smarter, that have more features built into it for end users that they want to use and they want to learn how to use in their day-to-day basis. So this Sentry fume hood display was kind of based on the size and functionality similar to a smartphone. So in the top portion of the screen up here, we actually have a touch screen built into it. So all of the functionality, the menu and things like that are all based on a touch screen. Down here in the bottom, again, safety being paramount for our products, we realize that when you're using fume hood displays or you're using fume hoods, you're probably going to have a glove on, and not all touchscreens react when you're wearing a glove. So we made the safety features, the fume hood exhaust, which is the emergency exhaust if you had a spill, and the mute function to be tactile buttons. So in the case that I had a spill and I needed to emergency exhaust my fume hood, I don't have to take my glove off to push the button. I guarantee that it's always going to work. So when I push that button, it's going to go to its emergency exhaust flow. The other thing that we did that was a vast improvement over what we had before is I'm giving the user a lot more information. So you can see here when I pushed emergency exhaust, the top portion of the screen turned red and it actually says emergency exhaust. Down here in this little information pane, it also says emergency exhaust, and it gives you a calculated face velocity where the sash is left right now. So it says emergency exhaust, face velocity 250 feet per minute. Now the reason we did this is if a customer has a chemist or somebody inside of the lab that has a question about why their fume hood has a high flow, most times they would have to call a maintenance guy. He would have to go into the building automation system to be able to pull up that point from this fume hood monitor and say, yeah, that's an emergency exhaust. Now the user can very clearly see this fume hood is in emergency exhaust. I need to take it out of emergency exhaust so that it will return to its normal flow. And then as the face velocity drops back down to normal, you can very clearly see that on the screen. So we added this energy meter on the screen to basically show when the fume hood is at its normal operation or when it's in setback. It has a relative range on there for your minimum to your maximum airflow, as well as the fact that it displays the face velocity, or it can display the flow as well. The other nice feature about these is you can also change the screen so it's just an active or an inactive alarm or normal condition. So the screen would just be green or red if it was normal or an alarm, or you can have the face velocity or the flow displayed on the screen. Some additional nice features that we added to this: if you go into the menu, you can add messages onto the screen. So there's some pre-built messages in here, or you can pick custom message. But when I select one of these messages and click OK, it can put a message on the screen. So if I'm an occupant of a wet chemistry lab and I decide that I don't want anybody to use this fume hood because I need to run a reaction for a couple of hours, I can actually put something like this on the screen where it'll say study in progress, or I can put do not use call and put my extension for my phone number on there, things like that. Again, trying to make this product more useful for the end user. The other feature that we added to this that's a real nice to have for an end use customer is the fact that we added a stopwatch timer in here. So a lot of times we would see these kitchen egg timers on the fume hood below the fume hood monitor where people would want to be timing a reaction. It beeps and they know they need to go check their fume hood. So realizing that people use that on a day-to-day basis, we decided to put that functionality into our fume hood display. So we have the ability to put a timer on here. You can hit start and go back out to your main screen, and it'll actually show the timer running right here. It'll have this little yellow bar will count down. When it's done, it'll actually show timer done. For now, I'm just going to go ahead and clear that. But again, that's another feature that we added to this to make it a little bit more user-friendly. This information pane down here that now says normal mode will actually give the user a lot more information than we ever gave them as well. So if I open the sash on this and this fume hood goes into setback mode, it'll actually say setback mode or normal mode. Because this is a network device, we can actually map things like outside air temperature or room temperature to the fume hood display. That information pane will also give you some alarm information as well. So in the case that I leave my sash open and walk away from my fume hood, so let me go ahead and do that. So I open my sash up, and currently I'm not standing in front of my fume hood. That information pane will actually generate an alarm called an energy waste alarm, which will get translated back to the building automation system. And basically what it's telling them is currently there is nobody occupying this fume hood and the sash has been left open. Now you can see that that face velocity dropped down to 60. Again, per ASHRAE standards, it's safe to have 60 feet per minute on an unoccupied fume hood and still contain the chemicals. However, I am wasting energy. So I'm sending a signal back through the Phoenix integration system back up to the building automation, telling them that I'm wasting energy on this particular fume hood. Now they can trend that and actually send it back to that employee and say, look, out of an 8-hour day when you're in the building, 5 hours out of the day you left your fume hood open and nobody was in front of that fume hood, so this is the amount of money that you're wasting. Again, a lot of these people are very green and very forward thinking, yet they don't realize that they're throwing hundreds of thousands of dollars a year away by leaving their sash open and walking away from it. So the nice thing about this, again, it says click to acknowledge alarm. When I click on it, it's actually going to say energy waste closed sash. So it's going to give me some information to try to correct my actions, as well as telling me when it happened. The other nice thing about this particular fume hood display, in addition to the energy waste alarm, it also has this feature called night energy waste alert. Basically what that means is if I shut off the lights in the room and the fume hood is unoccupied, then the sash being left open is wasting energy as well. So just like the energy waste alert when the sash is left open but nobody's occupying the hood, if I shut the lights off in the room, I know that the room is most likely not occupied. So if I shut the lights off in this room, and on my fume hood, now it's not only going to give me an energy waste alert, but it's also going to trigger a night waste energy alarm. And basically what that is saying is I left my sash open, I shut all the lights off and went home, and again, just like the standard energy waste alarm, I can trend this. I can send the information back up through the building automation system and actually try to change the habits of the users of the fume hood. So those are just some of the features of the new Century Fume Hood display. Just like the previous monitor that I used on the other wet chemistry lab with the smoke in it, this one also has the ability to go into hibernation mode. It's a little bit different method than the other one, but if I go in through the menu and the admin menu, punch in my password, and go into hibernation mode, it'll say, do you want to hibernate the hood, yes or no? I push yes, it says press OK to proceed, waiting for hibernate operation, and now you can see that it clearly shows the fume hood is in hibernation. Again, if I move my sash open, within a second that fume hood is going to respond and it's going to come out of hibernation mode and go back into its normal operation. So same functionality, plus a lot more inside this monitor versus what we had in the past. So now that we've talked a little bit about the fume hoods and the technology that we at Phoenix Controls have, I also want to talk a little bit about the entire envelope inside of a wet chemistry lab. And what I mean by an envelope is the pressure relationship between this space and the adjacent spaces. So the reason that this is important, a lot of times we hear about value engineering a job. It's very important to keep the cost low to the customer while providing them the best equipment that you can. Now the trap that a lot of people fall into in a wet chemistry lab is they say, well, you've proven to me that I need a 1-second speed of response on my fume hood, but I really think that I can get away with a VAV box or some other flow measurement device for my general exhaust and my supply air inside of this lab. They're much lower cost, and they're a little bit easier for somebody else that doesn't know much about airflow controls to configure. You just drop a K-factor into them and you measure the airflow and you're good to go. The problem with that is the reaction of those devices to the 1-second speed of response of a fume hood does not guarantee the pressurization in this space to stay stable. It also does not guarantee that the adjacent spaces will be stable either. When you think about an entire building as a pressure envelope, all of the pressures in the building need to equal each other or equal net zero. So if I have two rooms that are next to each other, one of them's positive by 100 CFM, the adjacent space should be negative by 100 CFM to make sure that both spaces balance out. This is why in a lot of buildings, when you go up to the front door and you open it, the doors are either blowing out or it's very hard to push them in because the buildings are incorrectly pressurized. So when you're looking at the pressure relationship with an adjacent space to a wet chemistry lab, the speed of response of these devices for the general exhaust and supply has to be the same as the fume hood. Otherwise, that pressure across the door is going to fluctuate, which could cause issues across the hallway. Now, if you keep your attention down here at the hula skirt on the bottom of the door, I'll demonstrate how that works. So right now I have my Phoenix Controls fume hood with a Phoenix Controls general exhaust and supply running inside of this space. And as I open and close my fume hood sash, you can see that my pressurization is always going to stay net negative. And in this particular space, I think we have the offset set at about 300 CFM negative because I have two doors in here. But as you can see, my hula skirt on the door is going to remain relatively constant, but it's always going to be flowing into the room, guaranteeing that I have negative pressurization in here. Now I also have a digital magnehelic gauge over the door, which you won't be able to see as I'm doing this demonstration, but I'm usually right around 0.03 negative on my airflow for my differential pressure. 0.025, 0.03 is my differential pressure. So that doesn't really change when I'm moving my sash up and down in Phoenix mode, because as fast as my fume hood is reacting, my general exhaust and supply are also reacting. The reason that works so well with our equipment, we have products that we built specifically for us. The actuators that we use are not an off-the-shelf actuator that you can go buy from a manufacturer. They're purposely built for Phoenix controls for the 1 second speed of response that we guarantee. So we put that 1 second actuator on our fume hoods. We also put it on our general exhaust and supply to guarantee that the zone balance inside of the room works in conjunction with itself. So as the fume hood opens, if my supply load doesn't change, my general exhaust is going to be inverse of that. My general exhaust is going to close. But it has to open and close at the same rate. So again, that's how we guarantee that speed of response. Now I can introduce a delay into this to simulate about a 15-second speed of response on some type of flow measurement device. So if you know anything about flow measurement devices, VAV boxes, or something that uses a bifurcated blade or something like that, any type of flow measurement device, not only is it not going to be as fast as a position-based device like Phoenix Controls uses, but it's also not going to be as stable. So in this demonstration, what we're simulating is a 15-second speed of response, which is a step speed of response, but this is also going to be more stable than what you would see in the field. So as I open my fume hood, I want you to pay attention again to the hula skirt. You're going to see that when I open my fume hood, it's going to be very negative in here for quite a long time. And as I close my sash, you're going to see that that hula skirt is actually going to go neutral and slightly negative and then slowly come back. So again, my pressure on my magnehelic gauge right now is settled out 0.02. As I open my sash, my pressure just spiked to 0.1, 0.12, 0.08, 0.07, 0.06. So not only did my pressure spike, meaning I'm pulling way more air into this space than I need to, so that also means that my adjacent spaces, my corridor and any rooms on the other side of the hallway, their pressurization is also being affected. But I settled out, roughly where I was before, 0.025, 0.022, something like that. But it took 15 seconds to get there. So if I had an issue happen in one of the other rooms at the same time I open this hood, there's a possibility that I'm going to get cross-contamination. Now again, conversely, when I close this hood, if you watch the hula skirt, it's actually going to go dead and slightly positive and then come back in. So there you see, my room just went positive for a couple of seconds. So if I had a spill in my fume hood, or if I dropped something on the floor and closed my sash very quickly, now those chemicals could have just washed out into the corridor, contaminating occupants inside the corridor as well as the adjacent spaces across the hallway. So that's why when you're looking at pressurization as a whole in a wet chemistry lab, all of the devices inside the lab should be at a 1 second speed of response to guarantee pressurization inside this space is maintained no matter what happens, as well as the adjacent spaces outside the corridor. Everything has to balance out to make sure that the entire system doesn't have cross-contamination and that you're going to have the most accurate and stable system that you can. We're now standing in the Phoenix Controls healthcare demonstration suites. Just like the research applications, we also have different various applications that the Phoenix Controls valves work in a healthcare environment. So the best things about healthcare environment using Phoenix valves is obviously the maintenance. In these type of environments, there's a lot of dust and particulate going through patient rooms and operating rooms, mainly because they're changing the bed linen so often. There's a big push in hospitals to make sure that you don't have products in there that require a lot of maintenance, because you have to put up these big curtains that have a fan sucking the air out of them. You have to go up into the ceiling, do whatever you need to do to clean the sensors out, pull that whole curtain system down, move it to the next box, and then put it back up and clean it. So it's been said before that in healthcare applications, if they had a maintenance plan and there was one guy going around cleaning all the sensors on all the VAV boxes throughout the year, by the time he finished the last box, he would have to start back on the first one because it's so time consuming to go through and maintain all those boxes. So again, Phoenix Controls valves, the fact that they need no maintenance because dust and lint does not harm them, makes them a really good option for healthcare environments. What I have behind me is a patient room with a special feature that we call Pandemic Ready Mode. Now, when we started developing healthcare products for the industry, we wanted to look at making products that were a lot easier for the users to program and get started up, because in essence, when you're starting a job, if you can reduce the startup time and the startup cost, you're going to save the customer money in the long run. So this pandemic ready mode that we have uses the tracking pair functionality that Phoenix Controls valve has, and in this particular application, we're actually using a supply valve, a general exhaust valve, and a return valve. Typically in hospitals and patient rooms, you're going to have a room with either a 3 or a 6 air change rate depending on occupied or unoccupied mode, and you're going to have that room set to be a neutral pressure. And again, that's just patient room. You just need a little bit of ventilation. You need to be able to guarantee that the patient is comfortable, that the humidity and temperature are working properly inside of that space. Now, when it comes to a patient that comes in, you may be testing them for something and you find out they have something that's contagious, or you find out their immune system is very weak. You need a room that you can very quickly change over to another function. So we came up with this pandemic ready mode, and in this particular application, the room would have, again, a supply valve, a general exhaust valve, and a return valve. In its normal state of operation, the supply valve and the return valve are tracking each other to maintain that neutral offset and just give the room the current temperature and safety that the occupant needs for that air change rate. If a patient is known to have a condition that needs to be isolated inside that space, you can have something similar to this. And again, this is a little bit dramatic to have this big button on the wall, but you can have a key switch, or you can have a button, or you can have a BMS writable command to trigger a pandemic mode inside of the space. Now, what happened when I just pushed that button is the supply valve is going to increase the air change rate in that room. The return valve is going to go into its shutoff position, and the general exhaust valve is going to open. So I increased the ventilation rate, I made the room negative, and I changed from 100% return air to 100% exhaust air without having to do anything other than flip a switch or send the BMS command to turn on pandemic mode. All of the programming that is done for that pandemic mode is part of Phoenix Controls valve controller. It does not have to be done in a standalone module or programmed by the BMS. We're strictly turning it off and on and setting up the variables for override flow, for the position of the general exhaust and supply, and for the offset in that space. It is all built into the Phoenix Controls valve controller. And again, that is a tracking pair application, so it's one valve controller actually controlling 3 valve bodies. Another healthcare application that Phoenix Controls products work very well in is isolation rooms and adjacent ante rooms. So what I have behind me is actually 2 rooms stacked on each other. This room in the back would be your isolation room, and this room in the middle would be your ante room. So this is going to effectively provide a barrier from the outside corridor and from the patient in the isolation room, so that you can have your wash down, wipe down inside the ante room, and then make sure that the patients are never contaminated. Now again, using a Phoenix Controls tracking pair for both of these spaces, we can guarantee the pressurization between the ante room and the patient room, and between the ante room and the corridor. So in many applications, you would have an ante room that is negative to the corridor, so all the air is being sucked into the ante room, and you would also have the patient room being negative to the ante room to make sure that all the contaminants that are out inside the general population would never make it into the patient room. But again, because Phoenix Controls has a tracking pair in the patient room and in the ante room, we can set up cascading pressure so that each space is more negative as you go in, or you can set it up so that the ante room would be positive in both directions, or that the isolation room would be positive in one direction and the ante room is negative to the adjacent corridor. Because each pressurization zone has its own tracking pair, you can effectively set up the pressurization any way that you need to. The last stop we have in our Phoenix Controls healthcare demonstration suite is the operating room. Now, the main concerns that happen inside of an operating room, again, going back to maintenance, making sure that whatever products are chosen to be put in here do not have to be maintained at all, because in this type of an environment, you really don't want to be shutting it down and cleaning sensors out every few months. Secondly, making sure that the pressurization inside the room remains constant at all times to guarantee the pressurization. So in this type of environment, again, we're using a Phoenix Controls tracking pair. We're using the Theris product line, which is our healthcare product line. And in here we have a supply Phoenix valve and an exhaust Phoenix valve. We also have some nailer terminal boxes on the other side of the room. So we have some unique setups in here where we have bubble tight dampers that will actually isolate either the Phoenix Controls side of the room or the terminal box side of the room, so that we can demonstrate how the two different products work in this type of an environment. And again, what we're trying to show the customer is not only do the Phoenix Controls products have the turn down ratio they want, so in this particular room we can go from about 200 to 1300 CFM on both the supply and general exhaust to make sure that the room can get the air changes it needs, but also make sure that as they transition from occupied to unoccupied, that they guarantee that the pressurization is always going to be constant inside of the space. So what I'm about to show you is the difference between how a Phoenix Controls valves work going from occupied to unoccupied and going from about 9 air changes up to about 30 air changes. And then I'll also show you how the terminal boxes do when they're using their flow measurement techniques to hold the pressurization steady. As I hope you can see from the video, the Phoenix Controls products provide the turn down that is necessary to maintain occupied and unoccupied flows in the space. They also will guarantee that the pressurization remains constant across the door, so that even transitioning from occupied to unoccupied modes, that I will never have reversion or the pressure flipping inside of the space. And I can also guarantee that they'll get there relatively quickly. So they're stable once they get to their set point. They're going to hold the pressurization more accurately. You don't have maintenance inside of this space. So Phoenix Controls products are always the best choice for healthcare. Another room that we have as part of our Phoenix Controls research demonstration suite is this life sciences lab. Now, over the past few years, we've noticed that research has been changing dramatically. We used to be very fume hood intensive in these wet chemistry applications, or for pharmaceutical manufacturing and things like that. There was a lot of wet chemistry hoods in those type of an application. So they would have very high air change rates in those labs. You'd have great turn down on your fume hoods and on your general exhaust and supply, and you also need to be able to maintain that speed of response. As life sciences started emerging, basically what that was a lot more open benchtop labs. So you didn't necessarily have wet chemistry fume hoods. You don't need that 1 second speed of response, but you still need to guarantee that you have the pressurization you needed for your space, that you're able to control your temperature in those type of spaces, and you need to make sure that your valves aren't going to get clogged up and dirty like a traditional sensor would. So we introduced these tracking pair applications in our TrackCell and our Theris tracking pair applications. Effectively what that means is, normally a Solaris system has one valve controller per valve. And that again is needed for that 1 second speed of response and to guarantee the speed of response of the network communications inside of the space. When you get into tracking pair applications like life sciences that I have behind me, most of the time the critical things that you need, again, is to maintain that the valves are going to track each other, so you have your offset set in that room, but otherwise really you're just doing temperature control, maybe humidification control, and you just need to make sure that your valves can get to their set points within a reasonable amount of time. So if you can have a lower speed of response, meaning a 25, 35, 40 second speed of response from your minimum set point to your maximum set point, it's a lot easier to do your control, and it's much more cost effective using one PCB for 2 or 3 valve bodies. So what I have behind me is a tracking pair application. It's our TrackCell tracking pair, which is our research line. And what I have in this particular room, behind me here, I have a 2-position vented cabinet. So it just has an occupancy switch on the door, which will send it from its shut-off position to a fixed airflow. And again, that's not a VAV hood. That is just a 2-position hood. So it's off and it's in a fixed position, and then it goes back to shut off when you're done using it. So on that particular fume hood, again, we have a Phoenix Controls low leakage shutoff. This type of a chemical containment hood would be used more for doing short-term experiments. If you're giving an animal shots or something like that, you need to make sure that they're in an vented enclosure to make sure that no odors get out to the general population in the building, or where you're just doing non-critical testing where you don't have a high concentration of chemicals or a high particulate count going through there. The rest of the system that is set up in this room, it's a supply valve with a tracking general exhaust. The way we achieve that with our tracking pair scenario is the supply valve is always going to have a circuit board on it, and it is actually going to contain the controls for the supply and the general exhaust valve. The general exhaust valve is hardwired back to the supply valve, and the way that it works, when the supply valve is driving the air changes up or down, the general exhaust valve will follow it in real time. And if at any point in time one of those 2 valves were to have a failure, if the wires got cut or the actuator shorted out or something like that, both valves are going to stop. So in that particular environment where you might be going from an unoccupied flow to an occupied flow, if you had a failure of one of the 2 devices, they're both going to stop moving. Therefore, at the last known position, you're going to guarantee the differential pressure of that space. Now, if you did have a failure like that, obviously you may not get to your full air change rate, but at least it'll give you an indication that, yes, my valves got to a certain point, they both stopped. Now I'm going to generate an alarm to tell the front end that I had an issue. However, I'm still going to guarantee that offset in that space while it's transitioning. As part of the Phoenix Controls research demonstration suites, I have behind me a biocontainment room. Now, what you see in this room may not be 100% typical of what you would see in every biocontainment room. However, we are trying to show a lot of the features of the Phoenix Controls equipment in the real environments where they would be acting. So what I have directly behind me is a large cage rack, an animal cage, and effectively how the Phoenix Controls product work with this cage rack is we have a special cage rack valve. And effectively what it is a valve that has a smaller inlet and outlet diameter so that you can put the hoses from that cage rack directly onto the top of the cage and right into the Phoenix Controls valve. This makes it a lot easier for people to install these in the field, and they work very well when you're using them with exhaust situations because, again, our valves don't get dirty with the dust and the lint building up on the valves. So in this particular environment, this would be great for a cage rack because you don't have to worry about the dust and the dander from the animals in their bedding getting into the sensors in a traditional product and clogging them up. We don't have sensors in our product, so therefore the Phoenix Controls valve works great in a cage rack. And in this particular environment, typically we would have exhaust on the cage racks, but we don't always do supply because these cage racks only use 50 or 60 CFM. And when you're trying to condition, heat and cool 50 or 60 CFM, it can be pretty difficult. So typically they're going to have some type of a filter for the air blowing into that, and the room itself is going to be used to condition that air. In addition to the cage rack we have in the space, I also have a biosafety cabinet over here, and effectively how the biosafety cabinet works in this environment is a recirculating hood with a filter and a blower in it. So the Phoenix Controls valve that we have on this is a shutoff valve, a low leakage shutoff valve, so that when this hood is in its shutoff mode and it's decontaminated, there is virtually no air going through that valve. The Phoenix Controls shutoff valves, when they're used in their low pressure applications, have a gasket on the cone, so when they're in shutoff mode, they leak 0.005 CFM. And we test the pressure on every single one of these when they're built. We use a pressure decay testing method to make sure that as they stay pressurized in shutoff mode, no pressure leaks through there. The way that it works on this particular biosafety cabinet is that when the hood is shut off, the valve is shut off in its closed position. When you push the button to turn the fan on to recirculate air in this particular hood, the Phoenix valve will start to open. The hood itself actually has a velocity probe built into it. So as that Phoenix valve starts to open, the velocity will increase through the hood. As that velocity probe senses airflow going across it, then the blower will turn on to guarantee that you're not going to blow the chemicals or whatever you're using in this hood out the front of the hood. Again, making sure that the safety of the occupant is always paramount in this type of a situation. In addition to the cage rack that we have in here and the biosafety cabinet, if you notice here on the wall we have a Phoenix Controls view. Above that we have an advanced pressure monitor. This has a pressure transducer built into it that's monitoring the differential pressure between the corridor outside the room and the pressure inside the room. Now traditionally when you're doing offset inside of a wet chemistry lab or non-critical or not as critical applications, you just have a fixed volumetric offset. So for wet chemistry labs you might have a -150 or a -200 CFM. Sometimes there's a rule of thumb that 10% of your total exhaust is a good starting point for your offset. Some people mandate 150 CFM or 100 CFM per door opening going in there. But in this type of an environment, because you're using biological chemicals potentially, or you're going to be doing testing on animals that may have no immune systems, you need to guarantee that those animals are safe. So instead of having a fixed volumetric offset, we're actually going to monitor the differential pressure across the door and vary the volumetric offset to maintain a differential pressure set point. The application that we use for that is called Progressive Offset Control, or POC. And how that effectively works, the pressure is being monitored from the transducer that's in this model here. It is actually hardwired back to the system on the Solaris 2 valve, and it's going to be looking at the differential pressure across the door and actually running a PID loop to increment the volumetric offset and maintain that differential pressure. So for example, in this particular room, I might have a negative differential pressure set point of 0.02 inches water column, and I need to maintain that at all times. So when the door is closed, no matter what's happening inside the space, if I'm taking that cage rack in and out, plugging up the airflow for that, or if I'm turning my biosafety cabinet on and off, I need to make sure that I always have negative pressure going into this room. So the advanced pressure monitor will read the differential pressure across the door. It will monitor the PID loop going in there that's controlling the volumetric offset, and it will actually vary the volumetric offset within a range to guarantee that I maintain that differential pressure. It also has alarm and trip points built into it, so if you need to alarm it to the building automation system or rewrite the differential pressure set point that the PID loop controls onto, all of that is integrated into the front end. And for this type of an environment, it works really well to guarantee the differential pressure remains constant at all times. Another feature of the progressive offset control is that this door actually has a door switch in the frame. That's going to serve two purposes. What it's going to do is when I open the door, I'm going to freeze the output to the PID loop, therefore I won't wind out to the extent of my PID. It will also introduce an alternate higher offset. So I know that when the doors open, I'm not going to be able to maintain my 0.03 differential pressure across the door. However, I can go from 175 CFM negative up to 350 CFM negative, and at least guarantee that I have directional airflow as long as the door is open. When I close that door, it'll notify the PID loop to pick up where it left off, and it'll send my offset back to its previous set point. So within 1 to 2 seconds of the door closing, you're right back in control where you were before, so you don't have spikes in your pressure while the door's opening and closing.